Great event, Amsterdam, perfect city.
Morning. So I think when, is it Ian who said about everyone glazes over when people start to talk, when he starts to talk about RF, well, give me 5 minutes and I'll start talking about lithium final chloride batteries. Just to introduce myself firstly, I'm Tom Willis, I'm from SAFT. We are a big French battery company. We're owned by Total, you know that name from the petrochemical industry. They bought us a couple of years ago. SAFT is a very big company in terms of some of our customers, like Airbus and Boeing and customers like this, but really it's in my division, civil electronics. We have different divisions, transport and grid, civil electronics, industrial standby, but civil electronics is kind of IoT, because many of the devices we've been making for many years are kind of linked to this market. I feel a little bit like IoT is a sort of semi-new name, but really the premise of those markets have been around for many years, whether it's in asset tracking or smart metering and what have you. And of course, across all of those markets, IoT really does join up lots and lots of individual minor markets. The biggest in the Netherlands, for example, is cows. I don't know if you're aware of that, but agriculturally, our biggest market in this country here, where we are today, is for cows. And just to give you the case study of that, we have something in the region of 7 million cows are born every year. It's an industry, it's a market. You might approve of things, you might not approve of certain things. But for cows, for example, for every cow that's born, they have a tag that's put on their ear. And with that tag, they can then track the cow, find the cow. But also, the big market there is also for immunization. Instead of giving every cow an injection that costs €100 per cow to prevent illnesses and so on, they can then see that that cow is not eating, or that cow has been lying down for 2 days, and then they can hopefully have a nicer life from not having lots and lots of injections and things. And honestly, when the life goes on a little bit longer and the cow's ready to go and say hello to the bull, then they know, because the hips move differently and everything moves differently and the circle of life is complete. So there you go. So you never thought today you'd have a presentation about how cows are made. But of course, within IoT, we, in the battery world, look at the chain from, we go from left to right. We look at our battery, and then we add on all of the things that you want to add in, whether it's your sensors, your wireless things, your chips, whatever it may be, your antennas, everything takes some power. But of course, nobody works that way. We want it to work left to right, but everybody else seems to work right to left. And then we have that holy grail thing of how many. We want all of this stuff, and we're going to give you this much space for a battery at the end, and that's when someone comes along and says, now I need that AA. But one thing's for sure from Mark's presentation, no, he's gone, from Mark's presentation, is really the battery becomes a critical component. Now, it's great for business, but it becomes a critical part of the application itself. But there's many things within the battery that aren't considered by engineers, and I'm not accusing anybody of not doing that, but things aren't considered because all too often people tend to use the battery at the beginning and they take almost a rudimentary analysis of the capacity of the battery and then work out their 5-year life. The 5 years is the thing that everybody wants, along with the reliability of that 5 years happening. But there's so many things that can impact that that are beyond just the straight up top line that this battery's got 2.7 ampere hours of capacity. And we'll come on to that. Now, before I move through the presentation, I should add that the presentation, as we've kind of drafted it for this event today, is kind of leaning a little bit towards, it's a little bit too leaning towards our sales of batteries. And the forum so far has been very informative in terms of more of a discussion piece, more information based. And so I will skip through a few things. But I'll come back to a few things as well. But I want to do it in the name of staying to the right theme of the event so far. And that's the one I'm going to skip. So just to talk a little bit just about batteries, we have to consider things beyond the overall capacity of the battery. Temperature. Temperature is so critical and can make a massive impact on how a battery performs or doesn't perform. For example, a battery in the Middle East will usually last approximately, and it's a bit of a sweeping statement, 20 to 25% for less life than a battery that's being used in, should we say, this part of Europe where we've got more of a moderate climate. Same if you go to the other direction, where if you go to something very, very cold, if you've got a cold environment, then you are going to have the same problems at the other end. So you want that kind of nice middle ground. But if you look on a battery data sheet, it will tell you that the battery capacity is whatever it might be, and it will operate from minus 40 to plus 85. Well, the reality is, like with many components and many things, the edges don't necessarily reflect what, the perfect scenario. So with temperature, you need to consider that, because then with temperature, a lot of the time, you have this phenomenon called passivation. I don't know if passivation is, if anybody's aware of passivation, but passivation is essentially a phenomenon within batteries which prevents it from self-discharging. A passivation is where you have a layer within the battery, and that layer will stop the battery from it's an organic thing. You can't really control it too well without doing lots of things to the chemistry. But passivation essentially stops the battery from discharging more than 1 or 2% per year. Now, it's a very boring subject, passivation, but I will just briefly run over it, because for example, a Duracell battery, a bread and butter, and I won't say a Duracell in case there's anyone from Duracell here, an alkaline battery at home, in your TV, remote control or whatever, will self-discharge to the tune of around 20% a year. And that's why on the side of that battery, there'll be a best before date or something. With a lithium battery, the passivation is down at 1 or 2%. And that means that you can then, when the battery is then brought to life, you have more capacity remaining, it will run for longer, then we're aiming towards that 5 years. But also passivation is something that needs to be considered, because some IoT devices are running at such low currents that actually the passivation isn't smashed away. It's almost like something you need to break. It's something you can physically remove it. So you need to consider that. Sometimes we have, with some of our IoT projects, we have in fact asked the people doing the embedded work to factor in or do a little bit of a boost just to bring the battery back a little bit, even though you don't need it for any of the items on the board, the chip or whatever it may be. We need it to kind of bring the battery back to life. So temperature, at high temperatures, passivation will occur more. We need to consider the average current, because that will affect the passivation, as I just sort of touched upon. The pulse intensity and duration will need to be considered, because again, they can break the passivation, or indeed, they can pull down the voltage. When you pull a current, the voltage goes down. And if your device is cutting off at 2.5 volts per unit, and it's a 3.6 volt battery, and it dips to 2 volts, then your device might say, hey, we're dead, we're finished. And it's not necessarily true. And again, that then links to the cutoff voltage of the device. Self-discharge needs to be considered, because there is that 1 or 2% a year. So if you have that, if you have a high rate of self-discharge, for example, in the Middle East, where you do go down a little bit further, and it's more 25% over 5 years, then of course that can affect the overall life of the battery. So there are more things to consider in terms of the battery than just a rudimentary what's the capacity and how long will it last for, and try and do the maths from that. And of course, both of these, the external parameters and the internal parameters will all determine how the battery actually does its job for you, because I don't want to make it all about me. I don't want to make it all about the battery. The device has got to work and perform and do the things that you want to do in the device that you're creating, or in the device that's out in the market, and you want that with reliability, with the life, and then we're all happy. So something Mark touched upon in his presentation, he was talking about how some of the suppliers will do project cases. This is what I do. This is basically what I do for my job. This is what I do all day, every day, is what we call product studies, where I will take I'll take the items that are within here and how it's being used to create an overall lifetime calculation based on temperature, based on current, based on the type of current, based on the strength of current, based on the voltage, based on temperature, and all of those things to give a very accurate analysis of how long that battery will last. Now, of course, we can never guarantee, we could never give you that rubber stamp of a guarantee to say, well, a battery is going to last for this long, because environmental things happen. If we base it on a 20-degree temperature and there's a heat wave, that's not my fault. We just have a nice summer. So we need to we can never guarantee things, but we need to consider things, and that's where we can come into play as a battery supplier. The battery is a critical component, but all too often it's being a little bit thought of at the end of the project. Now, just to quickly run through, and this is where I might trump Ian with the RF part on the glazing over. I'll just run through some chemistry. It's time to go back to school. Our bread and butter range for the Internet of Things is this one here, and that is lithium thionyl chloride. Now, just to explain, I don't want to patronize anybody in case I get this wrong, and I'm sorry if I do, but just to explain how a battery is made. You have a can, imagine a straight up can, and on the inside of that can you have some lithium. The lithium is like a foil, like aluminium foil, but it's on the inside edge of the can. And then inside of that you have a sponge, like a piece of licorice or something, but it's soaked with the electrolyte. And that's where your positive and negative are created. You have your, beg your pardon, too far. You have the lithium, then reacts with the thionyl chloride electrolyte, which is a kind of a gel or a paste that's soaked into this sponge, and then as they meet together, they react, they create energy, which creates voltage, which creates a battery. Now, lithium thionyl chloride is the main chemistry that you'll see in IoT applications. It probably accounts for about 80% of the applications. Thionyl chloride was actually invented by one of the engineers in SAFT, I think in the 60s or the 70s. It was actually created as a chemistry. I would say, without being too flippant, it is our bread and butter chemistry. It's 3.6 volts per cell, so that slightly higher voltage does mean that you can have a longer run life, particularly if you have kind of reasonably high cutoff voltage, and a lot of GSM applications do. And it's high energy for low power. We do have a range called LSH, which is like a spiral version. So it's not just a sponge within the can. You also have then a spiral, which means a bigger surface area, more power. So there are a couple of variants within that chemistry, but it is the main one. You see within that, and then the next chemistry, which is lithium manganese dioxide, we're always promoting within that 20-year life. Of course, 20-year life is a little bit marketing speak, because of course it's in the perfect conditions you'll get that 20-year life, and provided you don't take all the energy out of it too quickly. Now, with lithium manganese dioxide, that probably accounts for about 20% of IoT applications, because it's the big thing about lithium manganese dioxide, so it's the same lithium but slightly different mix on the electrolyte. The main difference being that the manganese dioxide as a phenomenon, it doesn't passivate, so you haven't got that build-up. So it will self-discharge more quickly, but you don't have to consider it for breaking that passivation layer away. So generally speaking, devices that are going to be more operating for 2 or 3 years will go to lithium manganese dioxide, or certainly devices that are going to be going through more of a maintenance cycle. For example, we have some asset tracking devices where, a lot in Germany, I think, where we have trailer tracking or to avoid trailer theft and things like this, where really the battery will be changed quite regularly anyway as part of routine maintenance. It just needs to work. Then we have lithium sulfur dioxide. This is traditionally a military grade. This is generally to be considered for high power, and the sort of device, if you have such a device, and I think it's probably not relevant considering what I'm hearing today, it's for devices that are doing nothing for like 5 years. For example, in military applications, if you have a tank where it's an emergency door, where you have to have the lights from green to red to say which way is up if the tank is rolling over somewhere in a war zone, that battery will never be used. But it might be one day, and when it does, it has to work immediately with high power for 5 minutes, and that's that. Now, there are some IoT-based applications, but I would say you're probably leaning more towards emergency-based applications or reactive, whereas a lot of the devices we're talking about today are more 5-year things that are just rolling and just moving and monitoring and sending that text message or whatever it may be. And then finally, we've got the high temperature thionyl chloride at the bottom here. This is kind of more for the downhole stuff. We do have some IoT projects for the oil and gas market where essentially the battery kind of commits suicide. It kind of goes down, it sends a text message, it says about the oil temperature or whatever it's doing, and then we never see it again. It's great for business because you can't ever have returns. Now, just to talk about the energy density thing, what everyone always wants is the most power in the smallest size for the longest amount of time. That really is what we refer to as energy density. How much can we squeeze into the fuel tank and safely? That's the big thing. And you can see here just from just it's a very basic chart, but alkaline is alkaline, it's bread and butter. It doesn't need to be energy dense. It doesn't need to have that because when your kid's toy stops working, you just grab some more batteries or you steal them out of something else and put them in. But within the other lithium chemistries where we need to work, you can see we start to come over in this direction, and you can see, it's not a very good graph this, but you can see that when we're talking about watt hours per kilo, that's really our how much bang for buck in terms of how much can we pack in. By far, lithium thionyl chloride is always going to be the winner, but these areas here still have a need, they have a purpose. But within that, someone was asking me earlier on about what other lithium chemistries are there, and the reality is there are loads of other lithium chemistries, but there's a big difference between a lithium chemistry that has even higher energy density that's kind of over here, but then you have no fingers left. So you have to harness energy density with safety, and safety is the critical part. If it's no good to be safe, then you can't ship it. You can't ship it, you can't ship your device, nobody wins. So the reality is that the most energy dense lithium battery you can buy, the most you can buy for your money, pound for pound, will be lithium thionyl chloride. I'm not saying from SAFT, I'm just saying lithium thionyl chloride is the chemistry that will always win that fight. There will always be a white paper, there will always be a Google article talking to me about the next big thing, the next big chemistry that's coming through, but they always fall down when it comes to the safety part. Now, I don't want to be too sales pitchy here because we as a company, where we do find ourselves in that fight against some other markets, some other Far Eastern battery manufacturers, is when it comes to the safety side of that. Because particularly in IoT applications, we're not just sending a battery to a manufacturer and the battery's just being used here and there, within that factory. Everything's going so far spread. I can't remember what Mark's number was, but you end up with that 1 in every 370 that needs to have a service engineer. Well, with a battery, the failure rate of a battery tends to be around 1 in every 1.5 million. But that 1 in every 1.5 million, you don't want that network to be so far spread with devices and passives that are just spread everywhere that the net goes too far to have unreliable batteries. I've got some business that I'm aware of that the company can never win because they can afford to have a 10% scrappage rate on batteries because they just grab another one and they carry on, but it's all in one factory. With IoT, the net's going very wide and fast, so reliability and quality become quite important parts. Now, just to touch on rechargeable, I would say that 95% of 85, 80, somewhere around this margin of products are primary. The 5-year life tends to be enough. The consumption is low enough that it can be a primary battery. As Mark said, you can then go into a primary battery pack, so you can multi-cell quite comfortably. And I think that the biggest one I have in IoT is a marine buoy that needs to send a certain signal, and it's got 40 D cells, so it's like a beer barrel. So generally, rechargeable is not required, but if it is, we have some pretty unique lithium ions. It's a little bit removed from the lithium ion that you might be able to see elsewhere, but we have what we call the MP, medium prismatic. It's like a small cigarette box type shape. And it's made with nickel metal cobalt aluminium technology. So basically that mix is like a paste that lithium, the electrolyte is spread onto the lithium and rolled up into what we call the jelly roll. And it's just highly reliable because you're less reliant on the battery being filled in a traditional way. I'm just going to touch on this today, but the one thing I did want to touch on is if you do find that there are ATEX applications, there are some very specialist ATEX grade batteries now for the hazardous, or what they call it, the HAZLOC, hazardous locations in the ATEX environments. It's very hard to get a battery that works, that fulfills the test criteria, because of course a battery is energy. You can make a battery short circuit quite comfortably, make it spark, and then you've got a problem. So for ATEX or hazardous environments, there are some batteries that we have within our range that are compliant to the standards that are required on those. It's quite a hard feat to achieve. Spent a lot of money developing that range to be able to make the battery almost so that it doesn't short circuit, and it's very hard to not make a battery short circuit. And again, within the energy density spread, you know, we like to feel we've kind of gone from all the way from left to right. Lead acid, the traditional kind of the sort of traditional battery you'd find in an alarm panel or something like that, is kind of all the way over here. So when you're kind of over on these edges, this is where the SAFT MP is. It's kind of on that kind of over 150 watt hours per kilo. So it's very, very energy dense, but less critical to be so energy dense because it's a rechargeable battery. It doesn't need to be you don't need to last the 5 years on one single charge like a primary. But still, you still want to have a good cycle life and achieve, and to achieve that, a good energy density can give you a couple of thousand cycles. Oh, beg your pardon. So, when we're talking about batteries, I think the theme of today from our side of things was to really consider the notion that not all chemistries are equal. I think people talk about a lithium battery. People talk about one chemistry. There's many different types of lithium chemistry. There's different levels of safety. There's different levels of energy density. And I would encourage anybody who's involved in speccing a battery to consider the battery earlier on, and to consider the battery as a critical part of what's going on. And also, unfortunately, that little battery that's that size, the size of a pea, that does 5 ampere hours of capacity and lasts for 400 years, it's not there yet. So we need to be considered maybe a little earlier on. The best way to do that is to engage. We're happy to engage. I would say that I was talking to one of the guys during the coffee break about when we're talking about LoRa, when we're talking about Sigfox, and we're talking about Raspberry Pi. We're a non-discrimination organization. We don't really care what's being used, but all of it needs some power. And so within that, we don't particularly mind what your application is or what's embedded on the board. But as Mark said on his presentations, it's good to root through so we can do the battery lifetime calculations properly, and then you can have that level of reliability. But as somebody said to me only yesterday, that they acknowledge that not all lithium batteries are made equal, and they are all different. So I would say just do consider it, and of course, and I would say just do your homework in terms of where you want your energy density to be, and please don't just work to the notion of using capacity as almost that's where you work from. Just to, I don't want this to be a sales pitch, but of course we have got all of those tools in place. We've got developers and engineers around the world who can do such lifetime calculations. We spend a lot of the money in the business on R&D so we can give good answers when we do these calculations for you. With the safety elements that go with the business, hopefully that can give some good options. Okay, so there's my contact details, and I've got some questions. I've been worried about this bit. What battery do you recommend for air freight tracking? Oh, no. Right. With air freight, there's a lot of bad information, and there's a lot of bad cowboys that are trying to make money from air freight. The problem we have is our batteries. Batteries in our world are what's classed as industrial batteries. Batteries like your iPhone they're classed as portable batteries. Portable batteries are completely left alone, and you can take them on the aeroplane, and every kid has, you know, an iPad and tablets and things. However, the regulations seem to be all on industrial batteries, as we have them. So, as of a couple of years ago, the rules were changed. You can't send anything by air freight, you know, under a plane now with passengers on board, but you can send nearly all batteries by cargo, DHL, you know, the yellow DHL plane, you can do that. So there's no, I would say, to answer the question terribly, there's no specific recommendation for air freight tracking, but most batteries you will find are Class 9, registered Class 9 dangerous goods, and they have to have a UN 38.3 certificate, which means that they are tested for transport. Doesn't mean they're not dangerous goods, because they are. They're volatile, they're powerful. But what they are is they're good for transport. But there are a lot of people out there that will, I have my own clients saying that they've got people trying to sell them special boxes and crates and things. It's a very mercenary market where people are trying to take from people's lack of knowledge, and they try and take advantage. So to answer the question, any battery that is UN 38.3 certified is good for air transport. I hope that answers the question of whoever asked it. What's the depreciation rate of your lithium rechargeable batteries per charge? Generally, if I'm doing a rechargeable product, the cycle life tends to be about 2,000 cycles. So the depreciation rate is, if you've got 2,000 cycles per year, well, it's a depreciation rate of X% for the year. But the reality is that there's so many parameters that go with that question. And I'm sorry that I'm not going to answer this very well, because with rechargeable batteries, it depends how you're using it, when you're using it, what temperatures in which you're using it, and how often you're using it. If you're talking about how many charges can you have, how many cycles, what's your cycle life, it depends how many times you're charging it per day. You know, how long will your iPhone last? Will it last for a year, or will it last for 5 years? It depends how you play with it and how often you play with it. But of course, if anyone wants to ask me more specifically, I'm very happy to answer that. Transportation of lithium is a logistical cost. What's the current situation? I'd probably need that question to be a little bit expanded, if that's okay. Does anyone have that question for me more specifically, or do you want to come back to me? Or hazardous goods? Yeah, is that kind of linked to the previous? Yeah, okay. If you want to ask me by all means. Can you transfer ATEX batteries by air? Yes. What about lithium battery disposal? What do we have to be aware of as manufacturers? Good question. Okay, in terms of disposal, there is the rules that were kind of implemented by the EU a few years ago were that tends to be the first legal owner of those batteries in that given country has the responsibility to get rid of the batteries if they come back. I will admit, not a lot of batteries get returned. They tend to just die in the field and they go, or wherever they go, but not a lot of batteries have been returned. If I tell you that I'm personally, in Europe, I think we're supplying something like 15, 20 million batteries per year, and the amount I see returned could fit in my car, no problem. It's just a small amount returns every year. But the responsibility would lie with the manufacturer of that unit. If you are the guy that's making that piece of equipment and you buy a SAFT battery or whatever battery, the responsibility is yours. But of course, as a battery manufacturer, we have all of the connectivity to make sure that the recycling can be done. So responsibility would be you as in manufacturer, but we are here to help on that. And I think that's the last of the questions, yeah? Okay, so unless there's any other questions, I'll thank you for your time. I hope I've given you some good information. I'm over there if anyone needs me for anything else, but other than that, thank you very much indeed.